So today's lab is a little different than the one that we did last year in this class. So last year in this class, Lab 6 was a radial traverse. One of the downsides of a radial traverse is that it provides no means of, or no straightforward means of correcting the data and whatnot. But I wanted a lab that had a very similar field experience, and that also gave you a little bit more familiarity with the calculations that we're going to do for the next couple of weeks, and that is going to be a resection. Okay. I want to explain the purpose of a resection right now. So everybody look up here. So this image might be a little hard to read here on the screen, but if you look in your handouts, that image is there in your handout as well. It's, I think, on page 3. So let me explain what a resection is. So if you go to Buskirk Field, and I'm going to show you some images of this here in a bit, there are a series of 4 nails that have been inset into the various pieces of concrete in Buskirk Field. And I know the precise X and Y coordinates of those nails. We're going to use 3 of them, specifically these 3 right here, and I'll show you pictures of them here in a second. We're going to use those coordinates combined with measurements that you're going to take in the field to determine the location, the X and Y coordinates of your total station, and the X and Y coordinates of an unknown target. Okay? And so the idea is we're going to reference known coordinates in order to determine unknown coordinates. And that process is called a resection. There are 2 ways of doing a resection. There's a 2-point resection and a 3-point resection. We're going to do the 3-point resection since all it takes is, to do the actual resection, all it takes is these coordinates and then 2 angles, which you will measure. Now this lab has 2 purposes. Again, it's to gain a little bit more familiarity with the equipment, namely the total station. I want you to get some familiarity with that, and as well with the associated math before we begin the traverse labs. There is a good chance that during this lab you might trip up, record a data point wrong and whatnot. That's sort of like okay. This is sort of like the first training wheels off lab with the total station. And that's okay because I want you to sort of shake the rust off this week so that when we start the traverse next week, we have a little bit more familiarity with things. I have 4, like I said, I have 4 control points in Buskirk Field, and I've named them control point 10, 11, 12, and 13. We are not going to use control point 11 for this lab. We're going to use 10, 12, and 13. The reason that we're using those is because I'll be upfront with you. The calculations to perform a resection are a little involved. And so some of those calculations I have already done for you. Okay? But in order for that to work, we have to all use the same coordinates. So what I mean by that, as an example, so like some of the calculations involve finding the distance between your control points. Well, I've already calculated that. I've already calculated these azimuths. I've already calculated these azimuths. So if we all use the same coordinates, then I've already done some of the math for everybody in here. So that's why we're all using the same ones. That's why we're not using control point 11. I have the X, Y, and Z coordinates for all of these points. I'm throwing some terminology out at you that you haven't seen before. So you'll hear the term northings and eastings really soon in class. Northings and eastings are just the land surveyor's term for X and Y coordinates. So northings and eastings and either heights or elevations. I have that for all of these points. The coordinate system that I'm using is arbitrary. So if you notice CP13, the coordinates, the X comma Y is 5,000, 5,000. So everything's referenced off that. I can reference off of that or what's called state plane coordinates. I have state plane coordinates for these as well. We'll talk more about that later. I'm not using state plane coordinates for this lab just because the actual numbers get really, really big. The coordinate system is much bigger. And so I'd rather deal with just numbers that are kind of a little bit more manageable for today's lab. First off, I want to show you pictures of the control points, and I've got flags next to them in Buskirk Field, assuming that they haven't been moved. So CP10 and CP11 are both next to these benches. I'm going to show you the image for CP11 because it's a little bit easier to see. So with both CP10 and 11, there's a bench right here, and there's this piece of concrete. If you look in the concrete, there's a little pipe sticking out. There's a nail set right here. So whenever you're taking your measurement, you want the point of that rod sitting right on that nail. Okay, that is the coordinate. Not next to the nail, not on the grass, right on the nail. Okay, that will ensure that you get accurate readings. We had a couple groups doing that during our last lab, so make sure the rod is on the nail. Okay, CP12 and CP13 are on these storm drains. So if you look at the storm drain, there is a sort of a lip of concrete around that storm drain, and the nail is inset in the concrete. Here's CP12, and here's CP13. Again, I got flags next to the control points. Just so everybody's aware, here are the control points. Okay, we are going to be setting up in these regions. I've already got the nails set, but given the activities on Buskirk Field with homecoming and the car right here that everybody's going to bust up and all that, so they put the car out there. That car looks kind of new. Like
it's not anymore. It's destroyed.
They've already
they're doing it.
Right now.
No
they're doing it.
Or doors.
They're doing it now.
Yeah, there's a lot of people out there.
It's
like
12.
That's why we were wondering if that's going to be a problem. Yeah, that's why that's going to be different today with everybody out there.
Yeah, there's a huge line.
I want to do it.
Okay, if we have to change gears and do this in Gullickson, I have coordinates in Gullickson as well. So we'll figure it out. No, we'll figure it out. But yes,
never mind.
Okay,
could be students.
There's a car there too.
Are you serious?
Pull the shit.
All right. Gotta love homecoming. All right, whether we do this in Buskirk or we do it in Gullickson, there are a couple things that I do want everybody to be aware of. The first is the angular measurement aspect of this. So we are going to be turning a total of 4 angles, and I want everybody paying attention to the words that are coming out of my mouth right now, because this is important. Okay, so the way this is going to work is, let's say you're the first nail, you're the second nail. Okay, so what you're going to do is sight the first nail, take a distance, what have you. Then you are going to go to the instrument, set the angle reading to 0, and then turn. Okay? What's going to happen is, here's why that is important. So let's say you're 0, 5, 10, 15, 20, 25, and let's say you're 85. Let's say it's 85 degrees. If you do not set to 0 when you turn to the next one, it's going to go 86, 87, 88, 89, 90. And so let's say from the first to the second nail is 85 degrees, and then from the second to the third nail is only 10 degrees. It's not going to say 10 degrees, it's going to say 95. And so when you record your data, it's all going to be wrong, right? So make sure that you set the horizontal angle to 0 before you turn your instrument. That's going to be important both for this lab and for the Traverse. Okay, so I'm really wanting to emphasize that. Make sure that you are always turning angles to the right. Okay, so we are taking a measurement, we are turning to the right, taking a measurement, turning to the right. Even if you have to turn all the way like that, you are turning to the right, okay, every time. Make sense? Okay. All right, for distance measurements, okay, so distance measurements, what we're going to do is we're going to collect all of the data. By default, when your total station takes a measurement, it will take all 3. It will take the horizontal distance, the vertical distance, and the slope distance. We're going to collect all of them. I will be upfront with you. We are not going to use all of those distances when we do the resection. The only thing that we're going to use for the resection and for the traverses is horizontal distances. The reason I'm having you record all of them is because, 1, I want you to gain familiarity with the instrument, and 2, we do need all 3 when we do the topo lab. In the topo lab, you need all 3 because you need elevations. So in order to do the topo lab, in order to do that properly, you need to record both the height of the instrument and the height of the rod. Technically not needed for a 2-dimensional resection, but again, we're going to do it because, again, part of this lab is to get you familiar with the equipment, okay? So I just want to make sure we're clear on that. When you set up your notes, I want everybody looking up here on this, because this was an interesting point of contention with the last lab. So what you should have is, so starting with the first nail to the second nail to the third nail to the target, back to the first nail. So between those, there are 4 angles, right? So see how Between the first nail and the second nail, there's an angle. Between the second nail and the third nail, there's an angle. Between this, there's an angle. Between this, there's an angle. Okay? There's a reason your notes are set up that way. There's even a screen capture of this table in your handout. Okay? So I didn't, Instagram pose for that picture a second ago, so I should have. But the idea is I want you to record that data in this fashion, because when we start doing our traverse computations, we're going to set it up in this fashion as well. Now, to each nail, we can record a horizontal, vertical, and slope. So from the instrument to the nail, distances. From the instrument to the nail, distances. So on and so forth. So for each point, there should be 3 distances, and between each point, there should be an angle. Okay? Now, this group actually chose, this is from data from yesterday, by the way. For this group, they actually chose to measure the distance to CP10 twice. So they started at CP10, did their measurements, went back to CP10, shot it again. Look, they're not the same, right? Right? Error. There's going to be error present in your lab. You don't have to do that. They did, but you can see that there's differences. Okay, so you're gonna see that today. Everybody's going to have some error present, and I want you to sort of get used to that with today's lab. Okay. The lab does require some in-depth computations, and I'm going to give you all that when we come back into the classroom. I want to also be upfront with you. We are doing a resection today by hand to get you familiar with the math and familiar with just the terms and the computations that we're going to see later. I'm just going to say it right now, because I'm sure people are going to ask, are you going to have to do a resection on an exam? No. Okay, so I'm doing this just to get you all familiar with these types of computations. Most total stations and data collectors can do a resection automatically. You do your shots, you hit a button, and it just does it for you. Because this is, because of the way I'm doing this, the handout I'm going to give you when you come back in has very detailed step-by-step instructions for how to do a resection. The one step that is a little cumbersome is step 5. The formula is a little wonky. So I've got a spreadsheet that will just do step 5 for you. So when you get to that point, come up here and I can help you with step 5. Your abilities as a land surveyor is not going to be measured by your ability to calculate the formula in step 5. One thing I do want to mention before we go outside is, and I said it in the last lab, and still nobody took advantage of this. You have this thing called Excel that will do a lot of the math, that will make a lot of the computations really nice for you. If you choose to use Excel, and it is something I do encourage if you're inclined, one thing to note about Excel is that it performs trigonometric calculations with radians by default. It doesn't work in degrees. So because we work in degrees, minutes, seconds, we have to properly convert to angles. So let's say I have an angle that's like 66 degrees, 44 minutes, 17 seconds. So I enter those 3 values into a cell. In order to calculate the decimal degrees, I just take the degrees plus the minutes over 60 plus the seconds over 3600 to get the degrees. And to get radians, I could multiply by pi over 180, or I could just use the radians command. So there's a formula in Excel called radians that will take the input and convert it to radians. Likewise, there's a formula in Excel called degrees that will convert the input into degrees. So those are some pretty handy formulas. But I do want to talk to you a little bit about converting back. So how would you convert back from decimal degrees to degree, minutes, seconds? So how do you do that? Let's think about how you do it by hand. So let's consider this angle, 79.4723 degrees. How do you convert that to degrees, minutes, second? How do you do it by hand? Well, there's going to be 70 degrees, 70 minutes, 70 seconds. I know it's going to be 79 degrees, right? I know that integer portion, 79, is going to be 79 degrees. What I can do is take this decimal portion. If I take this decimal portion and I multiply it by 60, I get 28 and some change. So I know it's 28 minutes. And if I take that change and multiply it by 60, I get 20.3 seconds. So this angle is going to be 79 degrees, 28 minutes, and about 20.3 seconds. Everybody know how to do that by hand, right? Everybody okay with that? So a way that you can do that in Excel is to use a particular function called round down. So the round down function will take sort of, however many decimal places you specify. So if you say round down, comma 3. It will round a value down to the third decimal place. So what we'll use is round down, comma 0. So it will round down to the units place. So if you had 79.4723, round it down to 0 and you get 79. If you take the difference of these two and multiply it by 60, round that down, you get the minutes. And then the same thing with that with the seconds. You could do that with the seconds. And I've given you a template here as well. That is a way that you can convert back from decimals, degrees to degrees, minutes, seconds in Excel. And what I'll say about Excel is, like, for example, I have a spreadsheet that will just do traverse computations for me. Took a while to build, but I don't ever have to do it again, you know. So Excel is your friend as an engineer, or a land surveyor, I guess I should say. Any questions?
Actually, I have a question.
Yes.
I was thinking about this. Do you make money from your YouTube account? You have a lot of subscribers.
This video is brought to you by Raid Shadow Legends. So.
Do you, have you ever gotten, a gold button or anything?
I have 60,000 subscribers, which I don't know how that happened because I'm not that interesting. But if I get 100,000, I get the button. So I don't.
I'll subscribe.
Yeah, so if I make 40,000 YouTube accounts,
Please, God.
If we get you to about 200 by the end of the semester, we all just get A's.
Oh, for God.
No.
we get like 5
I feel like
credit
that's a good
points.
deal.
If you reach 100,000 this semester, I think we all get like 4
I got a lot of friends.
I think that'd be fair.
All right, let's go to Buskirk Field and see how big the line is. So if we gotta shift gears and go to Gullickson, we will. So
Where's
I'm gonna,
Gullickson?
it's down the road.
Campus.
Down the road.
Do we need